Welcome to a lesson on the cubic bracket expansions. In this lesson, we're going to learn how to expand expressions that involve cubics. Now, before continuing any further with this lesson, I suggest you get familiar with expansions of powers of 2. I have a whole video on this that I've just linked, so I suggest you watch that first. I'll still be here when you're back. Now, just like I did in the last video, there are actually two types of cubic expansions that I want to show you. So I'm going to start by talking about the expansion of a plus b all to the power of 3. So as I've said here, if we want to expand a plus b all to the power of 3, we'd call this a binomial expansion. But instead of doing what we did for the power of 2, I'm going to use the result we got for the power of 2 to help us expand this much more easily. So we're going to start by saying that a plus b all cubed is the exact same thing as a plus b times a plus b all squared. Now that makes sense because you get two brackets from here and then the third one from here. Now since we know how to expand a plus b all squared already, I might as well just go ahead and expand it directly. We know that a plus b all squared is the same thing as a squared plus b squared plus 2 times a times b. Now after all of this, we just want to expand the whole right hand side to get our final expression. Now one way that we could do this is we could use the rainbow method of expansion. We could multiply each term one by one as I've shown over here. But instead I'm going to use a method that I've used a few times before, which is to draw an area that represents this expansion over here. Okay, so because I want to multiply a plus b times a squared plus 2ab plus b squared, I've drawn out a rectangle, and one of the sides is a plus b, then the other side is, predictably, a squared plus 2ab plus b squared. So therefore we can write the area out in 6 parts. This area over here is just a squared times a, which is a cubed. And then if we look carefully at these two areas over here, we notice something interesting about them. This one over here is a squared times b, so it's a squared b. Then this one over here is a times 2ab, so this is 2 times a squared b. And then we see the exact same thing with these two squares as well. Notice that this height is b and this is 2ab, so this is 2ab squared. Then this one over here is b squared times a, so this is a times b squared. And then this last missing area over here is just b times b squared, so it's b cubed. Now if you look carefully, we have an a cubed over here, but then we have a squared b's in both of these. Then after that we also have an ab squared here and also here, and then finally we have a b cubed over here. So given that we can draw things like this, then we can say that the expansion of this term is the same thing as a cubed plus 3a squared b's plus 2ab squareds plus 1b cubed. Now this formula over here is the binomial expansion of a plus b all to the power of 3. Now the way I remember it is you start off with an a cubed. Then you take a power from the a and give it to the b, so you're left with 2 on the a and 1 on the b. Then you repeat it again. You borrow another power from the a, giving it to the b, leaving you with only a to the power of 1. And then one more time, you take another power from the a and give it to the b, so you have 3 with the b and 0 with the a. But if you do this, you have to remember to put these 3's in the middle. This is sort of similar to the way that you put a 2 in the middle when you expanded a plus b all squared. So notice that in this case, because the powers are 2, you put an a squared and a b squared on the outside. In this case, since the power is 3, you put an a cubed and a b cubed on the outside. And because the power is 2, you have a 2 in the middle. And because this is a 3, you have 3's in the middle. Now after this, we should also deal with a case where this is a minus sign instead of a plus. To do this, all we need to do is replace all the b's for negative b's. So let me do that on another line. Okay, so now that we've done this, we just need to simplify the expression a little bit. So look at this term over here. Notice that these brackets don't really do anything, and we can just replace this with a minus b. Now we move on to the next negative b. If we look at this one over here, we notice that we can just take this minus sign outside of the brackets. So we're just going to end up with minus 3a squared b. Now let's turn our attention to the next bracket over here. Notice that whenever you square a negative number, you're always going to end up with a positive number. For example, negative 3 squared is just 9, so the negative just goes away. This means that we're going to end up with 3ab squared for this term over here. And finally, we look at this bracket over here. Notice that if you cube any negative number, it's going to stay negative. For example, minus 2 times minus 2 is positive 4, but then times minus 2 again gives you negative 8. So that means this negative sign is just going to come outside of the bracket, and you'll get negative b cubed. So therefore, when you have a minus b all cubed, you just expand it like this. Now, in case you struggle to remember this, just remember that b is going to be negative anywhere b has an odd power. So we just get minus signs in front of those terms. Now, I probably should show you how to use this, so let me bring up an example, and we can expand it together. Okay, so in this case, we'd like to expand 3x minus 2x squared all to the power of 3. Now, of course, we are going to need to use this formula over here because we have a minus sign. If you look carefully as well, you notice that 3x is the same thing as a, and then 2x squared is the same thing as b. So to complete this problem, we're just going to need to cube 3x, and then we're going to continually borrow a power just as we showed before. So I ran out of space a little, so I put this on a new line. But we can see that we've just applied the formula directly. Notice that we've cubed the first term, then subtracted 3 times the first term squared times the second term, then we've added 3 times the first term times the second term squared, and then we've subtracted the second term all to the power of 3. Now after this, we just simplify things by getting rid of all the brackets. So for example, 3 to the power of 3 is 27, and then you can write this whole term as 27x to the power of 3. Okay, now for the next term, let's look at the constants. 3 times 2 is the same thing as 6, and then we have to multiply 6 by 3 squared, which is 9. 6 times 9 is the same thing as 54. Now we just have to multiply x squared by x squared to get x to the power of 4. Now, if we look at the constants of the next term, we notice that we're multiplying 3 times 3 to get 9, and then we're multiplying 9 by 2 squared, which is 4. 9 times 4 is 36. Now we just have to deal with the x's. Notice that we can use the index laws here to say that this is going to be x to the power of 4. And then we have to add 1 because of this x, so you get x to the power of 5. Now we're looking at the last term. Notice that 2 cubed is the same thing as 8, and then x squared all to the power of 3 is the same thing as x to the power of 6. So we just get 8 times x to the power of 6. So therefore we can say that expanding 3x minus 2x squared all to the power of 3 leads to 27x cubed minus 54x to the 4 plus 36x to the 5 minus 8x to the 6. So that just about completes everything I want to say about the binomial expansion. Now I'd like to talk to you about another cubic bracket expansion that is also important to know about. In the previous lesson that I mentioned earlier, we talked about the differences of two squares. Now in this case, we'd like to talk about the sums and differences of two cubes. Now in the case of a difference of two squares, we had to cut one square out of another square. So it makes sense that if you want the differences of two cubes, we're going to end up cutting a cube out of another cube. So let me go ahead and draw this. Okay, so what I've drawn here is a larger cube whose sides are all equal to a. So this is a, this is a, and this is a. Now to find the volume of a cube, you just have to multiply all of the sides. So in this case, you've got a times a times a, or this a cubed over here. Now once we've done this, we then want to cut away a smaller cube over here, and we're going to say that its side lengths are all b. Now of course, the volume of this cube over here is just going to be the same thing as b cubed. So in a sense, we're subtracting the volume of this smaller cube from the volume of this larger cube over here. Now just like we did for the difference of two squares, we're going to break this remaining volume up into a bunch of parts. In this case, I'm going to break it up into 3 different parts. To begin with, I cut the whole area below our cube into a single section, as you can see over here. After this, I was left with this remaining volume over here. Then I decided to cut the back of it to get this rectangular prism over here. Then I've just gone ahead and color-coded the remaining area in this green over here. Now, the next thing I'd like to do is I'd like to unwrap all of these parts to make a single planar shape. So let me go ahead and start by actually pulling out the bottom. After this, I'm going to pull out this green piece at the front over here. And then finally, I'm going to pull out this blue piece that we had in the back over here. Now that we laid out the missing volume into this planar shape over here, it's actually pretty easy to find the total volume between these 2 shapes. We just need to work on finding the dimensions of this shape over here, and then it should be pretty straightforward to find the total volume, because it's just going to be the total area at the top multiplied by the height of the shape. Let's start by finding the volume of this shape over here. Let's begin by trying to find the height. Notice that the height here is a, and then we subtracted away b. That means this height from here to here is the same thing as a minus b. And that's going to be the height of this whole shape over here. After this, we notice that we're looking at the outer cube here. So this side over here is going to be a, just like this side. And this side over here is also going to be a because this side is a as well. Next, let's try to find the dimensions of this piece over here. We notice that this side over here is going to be a, just like this side is over here. This side, however, is going to be the same thing as b, as you can see here. This side is the same as this. Finally, let's turn our attention to this tiny piece over here. It's a little bit hard to see it because it's a little bit hidden behind our shape, but I'm drawing its outline in, as you can see here. Now, to find the dimensions of this piece, notice that this width over here is b because it's the same as the cube. And also, the height over here is also b because it's also the same as this smaller cube. So let's just start by finding the whole top area over here. The first thing we can say is that this area is the same thing as a squared because it's a times a. This area is the same thing as ab because it's a times b, and this area over here is b times b or b squared. So now if we just find the area of the whole top shape and multiply it by the height, we can find the volume of this whole shape over here. To find the area of the top, you just add up a squared, ab, and b squared. And then you're just going to multiply this by a minus b. So this brings us to our final formula here. We notice that a cubed minus b cubed is the sum of these 3 volumes over here. And it can be re-expressed as a minus b, which is this height, times a squared plus ab plus b squared, or a squared plus ab plus b squared. Now this is actually pretty similar to the difference of 2 squares. But it also has its differences. Notice that we're taking a squared minus b squared here. We get this same a minus b bracket, but then this second bracket is a little bit different. And that makes sense because cubes are a little bit more complicated than squares. However, unlike the difference of 2 squares, if we replace this b for a negative b, something quite interesting and a little bit unexpected happens. So as you can see, everywhere in the original expression where we had a b, I've replaced it for a negative b, as you can see here. Now it's pretty easy to simplify this, so let's do that. I want you to notice that negative b all cubed is the exact same thing as negative b cubed. For example, as we said before, negative 2 cubed is the same thing as negative 8. So we can pull this minus sign out and turn this into a plus. Now for this term over here, these brackets are actually unnecessary, and minus minus is the same thing as plus, so we can write this bracket as a plus b. After this, we look at this bracket again, and notice that this minus b can also come out to turn this into a negative sign. Now finally, minus b squared is the same thing as b squared, because any negative number squared turns into a positive number. For example, negative 3 squared is the same thing as 9, as we said before. So now, in a bit of a strange twist, we notice that it's actually possible to add up 2 cubes and get a formula that looks like this. it's very similar to the formula that we got up here. So if you ever forget this formula, you can just use some SOAP. SOAP is just an acronym to help you remember this. If this is a negative sign, then you choose the same sign first, then the opposite sign, and then you always use positive, SOAP. So notice here, you've got a positive, same sign, opposite, always positive. Now, of course, I'm going to show you how to use this, but before I do that, I just want to show you that this does not happen when we try this with the power of 2. So let me do that on a side note. So here I've just copied the equation for a difference of 2 squares. I'm going to start by actually replacing all the b's for minus b's. So for starters, I want you to notice that minus b squared is always the same thing as b squared. So we can just get rid of this minus sign over here, and then we just end up with a minus b squared, again. Now for this bracket over here, we don't need the brackets, so minus minus is just plus. We also don't need these brackets either, and plus minus is just minus, so let's replace those two. So something a little bit funny's happened here. Notice that we started with a squared minus b squared, then replaced all the b's for minus b's. After this, we just ended up with a squared minus b squared equals a plus b, a minus b. Whereas before we had a minus b times a plus b. Of course, you can always swap the order of multiplication, so we've just started with some formula and arrived at the exact same formula by repeating the same process. It turns out that it's impossible to construct a sum of 2 squares. It just can't be done. In fact, a little bit strangely, if this power was 4, it would still be impossible. If it was 6, it's still impossible. But it is possible to construct a power of 3, as we can see, and it turns out that a power of 5 is fine as well, and so is a power of 7. So in other words, it's impossible to construct a sum of 2 of anything where the power is even, and it's always possible to construct a sum when the power is odd. This isn't something I'm going to try to prove to you now, but I'm sure it's something you're going to be able to prove later on in your mathematical career. But for now, I'll just get rid of this working out, and I'm going to give you an example that we'll work through together that applies one of these formulas. So I'm just asking to apply the cubic formulas to this expression over here. Now, since we have a negative sign, we're going to use the difference of 2 cubes and not the sum. Whenever I'm trying to do this, I try to express both of these terms in terms of a cubic, so I'm going to have a bracket on the outside. Notice that 27 is the exact same thing as 3 to the power of 3, and 8 is the exact same thing as 2 to the power of 3, so we can rewrite them. Now after this, I hope you remember that we can pull this 3 out to write it on the outside. And then this term over here, we can also do the same, but this would be y squared on the inside. Okay, now we've got this in the form that we needed. This term over here is the same thing as a, and this term over here is the same thing as b. So let's go ahead and label them. Now that we've got it in this form, we should just go ahead and apply the formula directly. We're just going to get a minus b, a squared, plus ab, plus b squared. Remember, use SOAP. So in this case, we've just taken the first term and then the second term, and we've copied the same sign. Then we've squared the first term and then used the opposite sign. Then we multiplied the first and second term, and then used the positive sign because it's always positive, and then squared the last term. After this, we just want to simplify things. Notice that 3x all squared is the same thing as 9x squared. After this, we multiply this whole term to get 6xy squared. And then finally, 2y squared all squared is the same thing as 4y to the power of 4. And now this is our final answer here. Notice that if we apply the cubic formulas to 27x cubed minus 8y to the 6, we just get 3x minus 2y squared all times 9x squared plus 6xy squared plus 4y to the power of 4. If you tried actually expanding this, you should end up back here. So I do encourage you to try that, but you don't really have to. And that just about completes our example. So let's just summarize this lesson. So in this lesson, we first learned that if you expand a plus b all to the power of 3, you get a plus b times a squared plus 2ab plus b squared. We then saw that if you swap b for minus b, you can also write it in this form here, which is a cubed minus 3a squared b plus 3ab squared minus b cubed. notice that whenever the power is odd, we get a negative sign. We then turned our attention to the difference of two cubes, which is the volume of this outer cube minus the volume of this inner cube. We found the difference of two cubes by rearranging these three blocks into this shape over here, and then found that you can rewrite it as a minus b all times a squared plus ab plus b squared. When we replaced b for minus b this time, we found the sum of two cubes, which is the same thing as a plus b times a squared minus ab plus b squared. We then also talked about the SOAP acronym, which says that if you have a negative sign, you choose the same sign first, then the opposite sign, then you always use positive at the end. We also briefly mentioned that it's impossible to find a sum of two squares, but you can find a difference of two squares. Now, as we said in a previous lesson, formulas are designed to save you time. You could always take this, draw the volume, rearrange it like this, and then find this side over here. But instead of doing that, you can just jump from here right to here. In general, if we've done the work once, we don't have to keep doing it over and over again. And that's all I'm going to say about the cubic bracket expansions. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.